Okay, let's go ahead and get started. So, today we're going to start in on probability, which we've actually already talked about a little bit. Towards the beginning of the semester, we had an experiment that we did having to do with probability where we flipped a coin about 50 times. And then we also had somebody else pretending to flip a coin and recording results. And the outcome there, we compared the two sheets to see if they looked similar. So do actual coin flips look like what we expect them to look like? You know, if we just kind of make up results, does it look the same? The answer is no, they don't look the same. So what we expect to see when we flip coins and roll die and things like that is that they're going to be pretty normally distributed results. So I think if I did the same experiment with this die instead of a coin, you know, the person making up the results might include every single number if they roll it 50 times or pretend to roll it 50 times. But is that what we would see if we actually rolled this 50 times? Probably not. You know, we'd probably have a lot of the same number occurring. You know, we might have a lot of threes, we might have a lot of fours, and they might have them all in a row. And again, is every single number going to be represented? Maybe not. It's possible that all the numbers will be represented, but it's also quite possible that they won't. Okay? So, let's actually go into probability and learn a little bit more about the particulars of probability. Okay, so actually, let's start with this die here. Okay, this is a normal six-sided die. It's got all the numbers from 1 to 6. Okay, so the most basic question we can ask is something like, what's the probability of me rolling a 1? 1 out of 6, good, yeah. The reason we say that is because we want to compare the total possible outcomes to the one that we want. Okay? So we would say that the probability here is that we have one outcome that is what we want. So it's the 1 there. There's only one of these things on this die that is what we want. And then all the things on the die there's 6 things. So it's a 1 out of 6. It's very much like when we were working with that problem on the exam that had to do with the phone company and the complaints. And we had to calculate the percent of the complaints that were in a particular category. We were dealing with frequencies, and that's essentially what this is. It's like frequencies. So 1 out of 6 of these is going to be favorable, and we can turn this into a percent just like we were doing with that problem on the exam. So we can do 1 divided by 6 and then multiply by 100. And so the percent chance of rolling a 1 would be, let's see, 16.7. So if we were to roll this 100 times, we could expect maybe 16 of them would be the number that we want, 1. Okay? And we can keep increasing this. So like out of 1,000 times, what would be the chance? So that'd be 1,000 out of 6,000 be the same exact percent chance. Okay? Does this make sense? So no matter how many times we roll this, it's always going to be the same percent chance. So whether it be 1 out of 6, 1,000 out of 6,000, 1 million out of 6 million, however many times we roll it, it's always going to be the same percent chance. It's always going to tend toward that result. Okay, so 1 out of 6, the most basic way. Now, are we guaranteed to get 1 if we roll this 6 times?
No.
Just like we were saying, no. We can roll this, let's see, 1, 2, 3, 4, 5, 6, and actually, yeah, we didn't get a 1 that time. But the more we roll this, the more it's going to tend towards this. So 16%, or maybe even 17% of the results will be the number that we want, the more we roll it. Okay, and that has to do with iterations. So, for instance, if you play the lottery once, what's your, how likely is it that you're going to win?
Not very likely.
Not very likely at all. In fact, if you keep on playing the lottery, still not going to be very likely. Okay, the best way to try to win the lottery is to buy more tickets. So if you, in 1 week, buy like 50 tickets, you're going to have a better chance at winning the lottery. Or if you buy like 100 tickets, the more iterations, the better the chance. Okay? Any questions? All right. So let's keep looking at this die and do some other things. So what's the chance of me rolling an even number? Yeah. So again, it's the favorable outcomes over the total outcomes. So how many even numbers are on this die?
3.
There's 3 of them, yeah. And of course, there's still 6 possible outcomes. So it's a 3 in 6 chance, or like you said, 1/2. Perfect. So 1/2 chance, or as a decimal, of course, that's what? Or I'm sorry, as a fraction, it's what?
1/5.
It's a 50%.
Oh, well, right.
Yeah, but 0.5 would be the decimal. So 50 times 100, we could expect to get an even number. Okay, what about an odd number?
Still 3 out of 6.
Yeah, still 3 out of 6. Good. Okay. How about, what is the probability that I would roll greater than 4? 2 out of 6, yeah. Good. 1/4? You bet it again.
I mean 1/3.
1/3. Okay, and so as a percent, what would that be? 1/4 is 25%. What's 1 divided by 3? 1 divided by 3 is, whoops, 1 divided by 3. It's 33.3%. Basically, it's a repeating decimal. Okay, good. Any questions so far? Okay, this is really, really basic probability. And we can make this a little bit more interesting by adding another die. Or, I'm going to make a different one. This one's easier to read. Okay, so this is a normal 6-sided die, something you're probably used to seeing. This is an 8-sided die. Okay, so now instead of rolling one die, let's roll both of these. So let's say I want to roll a 5 on this one and a 3. Where's the 3? Yeah, a 3 on this one. So I want to roll both of these at the same time, but I want a 5 on this one and a 3 on this one.
So the probability is 2 over 14.
Okay. Do you have a guess? No? Okay. Let's think about it a little bit more carefully, though.
Because wouldn't you, on one die there's 6, on the other die there's 8, so So if you combine those, you combine the 14, and then you want one on each, so you combine those, which is 2, and 32 over 16.
But you gotta remember something about this. True, this one has 6 outcomes. We can get a 1, 2, 3, 4, 5, or 6. This one has 8 outcomes. 1, 2, 3, 4, 5, 6, 7, 8 outcomes. Okay? Now, if we were rolling these separately, yes, there would be 6 possible outcomes there, maybe 6 possible outcomes here, but we're rolling them together. So, we have to remember that if I roll like a 1 on this one, how many other numbers can this number be paired with? How many numbers can I pair 1 with?
8.
There's 8 different numbers that I can pair 1 with. How about 2? How many numbers can I pair 2 with? 8. In fact, each of these can be paired with 8. So if I roll a certain number on here, there's 8 different numbers that could come up on here. So we have, let's see, 8, 16, 32, wait, no, I'm sorry, 24, 32, so on and so forth. In fact, actually what we need to do here to get our total outcomes is multiply these together. Okay? So again, for each of these, there's 8. And since I have 6 of them, that's 8 plus 8 plus 8 plus 8 plus 8, so I have 6 8s here. So 6 times 8 is the total outcomes possible here. What is 6 times 8? 48. So there's actually 48 possible outcomes for this. All right, well, what's the probability of me rolling again, a 5 on this die? What's the probability of rolling a 5? Yeah, just on that one. Probability of rolling a 5. 1 out of 6. Probability of me rolling a 3 on this one. 1 out of 8. So we have a probability of 1 out of 6. I'm sorry, shoot. 1 out of 6 on that, and a probability of 1 out of 8 on this one. Again, if we want to know our total probability, we need to multiply these. So what is 1 times 1? 1. And 6 times 8? 48. So the total probability here is 1 out of 48. Because there's only one way for these to have a 5 on this one and a 3 on this one. Right? There's only one possible way for me to roll this and get a 5 on this and then a 3 on this. And then how many total possible outcomes are there? There's 48. So it's 1 out of 48. Does that make sense? Yeah? Okay. Okay, so again, probability doesn't always work the way that we think. In fact, you're not the first person to say that answer for this one. Every single class has had someone that says that. Because, again, probability does not work the way that we usually think. We have to look a little bit deeper. So, thank you for saying that. Okay. Let's look at some more. Maybe I want to roll, let's take some simpler ones. This is a 4-sided die, it has 4 possible outcomes. Maybe I want to roll these 2, and I want to get a sum that is 8 or greater. So 8 or more.
So on the 4-sided die, how do you know what number?
That'd be the number that's on the bottom. It's hard to see because the way that this is angled. But see how this 4 is on the bottom?
Oh, okay.
Yeah. Okay, so I want to know what would give me an 8 or greater. Well, again, how many total possible outcomes are there? Well, this one's 6 and this one's 4. So what do I do to find the total possible outcomes? Is what? Multiply, yeah. So 6 times 4. So there's 24 possible outcomes if I roll these two die together. Okay, now, how many outcomes will give me 8 or greater? Okay, well, let's think about it.
Well, if it's a four-sided die.
It's a four-sided die.
No, then what are we doing greater than what?
We want to roll both of these and have a sum, so add the two outcomes, yeah. So, for instance, maybe we roll a 4 and a 4. That would give us 8. That would be a favorable outcome, right? So, for 4, if I roll a 4 on this one, I would need to roll a 4 on this one, right? To get an 8. Okay, now could I roll anything else on this one to get an 8 or greater? Yeah, this one doesn't have 5. And 4 plus 3 is 7. 4 plus 1 is 5. 4 plus 2 is 6. So yeah, if I roll a 4 on this one, the only possible thing for me to get that would satisfy us here would be a 4 here. Okay. What if I roll a 5? What would give me 8 or greater on here? Okay, so 3 would work. Or what would be also acceptable? 4. Because 4 plus 5 is 9, and that's greater than 8. And we want something equal to or greater than 8. Okay? But those are the only two, right? Okay, so what if I roll a 6 on this die? Find the 6 real quick. What could I roll on this to make it work? 2 or greater. Good. You're getting it. So I could roll a 2, a 3, or a 4. Okay. All right. Now, are there any other possible outcomes that would work here? Would anything else give us an 8 or greater? The answer is no. And we can tell because of the pattern that's emerging here. So the smallest number on here that would work to give us an 8 total is 4, right? That's the smallest one. And so the only thing that would give us a 4 here is another 4. So that's one possibility. Next would be 5, and it has 2 possibilities. Next would be 6, and it has 3 possibilities. And we can't go higher than that on this die. But again, notice that pattern. 1, 2, 3 possibilities. It's going to come up in a minute here. Okay. So how many do we have? 1, 2, 3, 4, 5, 6 ways that we could roll an 8 or greater. And again, how many total possibilities are there? 24. So 6 out of 24. All right. What is 6 out of 24 reduced? 1 and 4, yeah. And this one, as a percent, is what? 25%, good. All right. Excellent. Any questions? Nope, makes sense. All right. So again, this is very simple probability. So if we have one thing that we're doing, we can just kind of say, okay, what's the number of favorable outcomes? and how many outcomes are possible. Okay? Pretty simple. Once we start doing more than one thing, we need to start combining these probabilities. This is what's called compound probability. And in compound probability, you find the probability of the first one and multiply it by the probability of the second one. So let's try something slightly different. No die this time. I wish I'd brought my deck of cards, but I forgot it. But let's say that we have a deck of cards. How many cards are in a deck? 52. Standard deck is 52 cards. Okay? Now, let's say I want to pull a club. Doesn't matter which club I pull, I just want to pull one of the clubs at random. Well, how many clubs are there? Not just the face cards, but the number cards as well. So we have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then jack, queen, king, right? So how many is that? 13, right? Yeah. So it's 13 clubs in a deck. So if I want to pull a club from my deck at random, it's a 13 out of 52 chance, right? Okay. Let's say on the next one, I've already pulled a club, and I want to pull a second club. I want to do it twice in a row. So we have a new probability, so I've got to multiply our original one by the next one. What's the probability now that I pull another club? Well, how many cards are left?
12.
There's 12 clubs left. And how many cards left in the deck? 51. Good. I want to do it again.
13 out of 50. I mean, 11 out of 50.
11 out of 50. Good. And of course, it would keep going on and on like this
10 out of 49.
until we have,
0 out of.
well, it'd be 1 out of,
Oh, yeah, one of those.
well, it's 52 minus 13. 39. Okay? So, if I want to pull every single one of those clubs out, all in a row, without pulling out anything else, this probability is going to get multiplied over and over and over, so it's going to get more and more, or I should say less and less likely. So for instance, 13 out of 52, it's easy to understand, it's 13 out of 52 chance. What about the second time? Well, that'd be 13 times 12, that's 156, out of, let's see, 52 times 51, that's already pretty big, 2,652. If I want to do it that third time, I need to multiply this by the next one. So 11 times 156, that's 1,716 out of, oh man, this is going to be big. Let's see, 2,652 times 50. Whew. That's 132,600. And just so that we can understand these a little bit more, let's get the percents for them. So 13 out of 52 is going to be, wow, really? Huh. This is a 1 in 4 chance. Okay, so that's 25%, apparently. 156 out of 2,652 is a, wow, 5.8% chance. And then this next one, out of 132,600 is a 1.3% chance. So as we keep on trying to pull more and more of these clubs out of this deck, our chances go from 25% to about 6% to 1%, and it's going to keep getting lower and lower and lower as we approach our last card. Okay, any questions? None? Okay, I want you to look at something here real quick. We have 13 times 12 times 11 times really what would be 10, then 9, then 8, then 7, 6, all the way down to 1. Okay, and really the bottom part does that as well. Not as clearly, I'll show you what I mean in a minute, but the top part very clearly goes 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12 times 13. There's a name for this kind of progression, and that is a factorial. So a factorial is something like 4 factorial. This exclamation mark means factorial. And what this means you need to do with it is multiply 1 times 2 times 3 times 4. Okay, so 1 times 2 times 3 times 4 is, anybody know? 24. Okay. Next one up, 5 factorial. Be 24 times 5. That's 120. 6 factorial be 120 times 6. Think you got it?
No.
Huh?
Oh, yeah.
Okay, it's 720. Notice that these are increasing quite quickly. Okay, so these are iterations, like I was talking about before. The more you do something, the more that. Okay. These are actually quite useful in certain places. Particularly, the one that I can think of right off the bat is security. Okay? Locks are based off of these numbers. So, like a combination lock, it's got a dial on it, right? And you spin that dial to put in certain numbers. Okay, well, what that's doing is you're organizing the numbers on that lock into certain slots for your password, for your code, right? Okay. Now, in order for us to know how many different types of passwords there are, so how many different outcomes for passwords there are, we need to do iterations. And it comes out with these factorials. So let me show you some examples. First of all, we need to understand how our combination actually works. So, like your locker in high school probably had one of these dials on it, right? So how many numbers were on that dial? Yours was 60. It's pretty common. Anybody else have a different number?
Some of the ones that like was four-sided, but not four-sided, but like have that 1,
The-
2, 3, 4.
Yeah, yeah.
Up, down, left, Right.
Yeah, okay. So that's another combination. And we can do that one also. But the one that I've been talking about today is the 100 number dial, which seems like a pretty secure dial when there's 100 numbers that you have to choose from. Okay, and then typically, how many numbers are going to be on your code?
4 or 5.
4 or 5. The
Well,
one.
This is a regular one, but in this one, there's not to do that. Like I said, flip one.
I'm talking about like when you put your code in, how many numbers are in that code? It's a 3. Typically, what you see on these dials, you can also have the ones that are 4 or 5. And I'm going to get into why they do 4 and 5 in a minute, because that's actually an interesting thing to bring up. So, code has 3 numbers in it. So what we're doing here with these combinations is organizing 100 numbers into 3 possible slots. And not just that, but the way that we organize them into these 3 slots matters, because the order matters. A combination of 1, 2, 3 is different from a combination of 3, 2, 1, right? You don't want a lock that you can put in 3, 2, 1 and have it be the same as putting in 1, 2, 3. In fact, combination locks should be called permutation locks. Okay? So a permutation is one of these things where we're trying to order events into particular slots, and order matters. That's important to remember with these. Order matters. Okay? So here's how a permutation works. It's got a formula behind it. It's NPR equals N factorial over N minus R factorial. Okay? So N and R are the things that we're trying to organize and the slots we're organizing them into. So N is the number of possible events, or the number of things that could happen. And R is the slots we're organizing those into. So for instance, like if we have people running a race, the number of people running in that race would be N, and first, second, and third place would be R. Okay? But in this case, we have 100 numbers on our dial, that's our N, and the code is 3 digits long, that's our R. So we'll just fill these into our numbers here. Whoops. 100 P3. P is just name of this thing. It's permutation, showing us that it's a permutation we're doing. Okay. So we have 100 factorial over 100 minus 3 factorial. So following order of operations, what's the first thing we need to do here? What's the first step in order of operations? Not multiply, it's actually over there on the board. Yeah, that's our order of operations, so what's the first step there? Grouping symbols, or parentheses, whatever you want to call them. So we need to do what's in the parentheses first. Yeah, what does that give us? 97? Okay.
And then exponents, so
Now we don't have any exponents.
ND, right, that's one
Okay, so we have division. Okay, now remember that we also have multiplication because these factorial things split this up into multiplication. So this is 1 times 2 times 3 times 4 times 5 times 6 all the way to 100. And that's a lot of stuff to enter into a calculator, isn't it? There's a better way to do it. So keep in mind that yes, indeed, this is 1 times 2 times 3 times 4 all the way up to 100. And 97 is the same thing, 1 times 2 times 3 times 4 all the way to 97. Okay, so we have numbers that are multiplying on top and bottom. But between these numbers we have division. So what that means is we can cancel the common numbers. So anything that is common between top and bottom, we can cancel out. So 1 cancels, 2 cancels, 3 cancels, 4 cancels, all the way up to 97, because those are the numbers they have in common. So if they cancel all those numbers, all we have left on top is 98, 99, and 100. Make sense? Okay, so that's easy to put in. So again, 98 times 99 times 100 is 970,200. So, on a 100 number dial with a 3-number code, that lock has 970,200 different combos that you can put onto it. That's how many codes you can put on. So guessing that code would be a 1 in 970,200 chance. Seems like it'd be pretty hard to guess, huh? Actually, if you are experienced in code cracking, it's not very big. In fact, those lockers, they're basically set up so that average student walking down the hall isn't going to be able to open it. But if someone who's experienced really wants to get into this thing, they're going to get into it. Okay? So the question is, how do we increase the security on this?
Put it down in the hole.
We could, yeah. But how do we make a better lock?
Put your own code in.
Well, again, your code would be one of these 970,200 numbers. So that's not increasing. We want this to be a bigger number. The bigger this bottom number is, the better the lock is. So what we could do is we could either increase the N or the R or both. But which one is more effective? Is it more effective to increase the N or is it more effective to increase the R? In other words, is it more effective to increase the amount of numbers you can choose from, or is it more effective to make a longer code? Okay, let's see. Because I think most people would say, yeah, it's more effective to increase the amount of numbers that you can choose from. I mean, after all, if we look at internet passwords, what do they want you to put into your password? Things like numbers, symbols, capitals, things like that, right? So that's increasing the amount of things that you can put into your code. It's not increasing the size of your code, it's just increasing the things that you can put in. So tell you what, so that we can compare this, instead of having 103, let's multiply n by 10. Let's make it 1,003. So again, I've multiplied this by 10 to make 1,000 instead of 100. Now, to save us some time, I'm going to just put this into my calculator and get the answer. So, luckily for us, the calculator actually has a function for permutation. You go to math, and then scroll over to probability, and there it is right there, NPR. So we will put in 1,000 for our n, and we're going to keep 3 for our R. Again, our code is only going to be 3 numbers long, but now we can choose from 1,000 different numbers. Okay, and this is how many different codes we can come up with now. So that is, let's see. Yes. Yeah, good. So 997,002,000, whoops, forgot a 0. 2,000 different passwords that you can come up with for this lock now, by increasing this by a factor of 10. Well, that's definitely bigger than the 970,000 that we had before.
So next year, the other one was not have to put the number back at 100 and then change the R
To what?
increase it by 10 to 13.
Increase it by a factor of 10, so multiply it by 10, so 30. But perfect, yes. So now let's go back to this being 100, and then instead of multiplying this one by 10, multiply this one by 10 to make it 30. So now we've got a 30 character long password. Let's see what that one comes up with. Okay, so make this 30 now. Oh, I still have it at 1,000, sorry, yeah, you're right.
Whenever it breaks up and it doesn't mean like it's continuous record.
What it means is that it's scientific notation, so let me write this appropriately. 7.79 times 10 to the 57th power. What this means is that we would move this decimal to get a normal number
57 times.
57 times this direction.
So that's a way bigger number.
That's an astronomically big number. I mean, I don't think I could write this number and have it fit on the page. It's huge. And so, yeah, we can have 1,000 things that we can choose from, and it does increase our security a little bit. But if we just make our password slightly longer, it's actually quite a lot more secure. So yeah, talking about the passwords for internet stuff, you know, we have to have these special characters and these capitals and numbers and things like that. And that's because people think, well, if you have more things to choose from, it's going to be a harder code. Which is true. It is a harder code. But if you just make your password a little bit longer, it makes it a super secure code. So the answer is, it's actually a combination of both. You can make a bigger N, and it will increase your security, but the R is really the one that has the power behind it. Having a longer password makes it harder to crack. It's the same thing with keys. So if you have a key, let's see if I have my keys. So if you have a key, it's got these bumps on it. Bring it up to the camera a little bit. Each of these bumps is an N. So let's see, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, I think, N. So our N is 9. I'm sorry, R is 9. And then the height of that bump is the N. So the longer your key, the more bumps it has, the bigger your R, the more secure it is. So this is more secure than maybe something like this. This is just the key that I use for my storage room. So not anywhere close to as many bumps on it, so it's not as secure. Okay, so all of these locks and security things work this way. Any questions? None? All right, well, I think that'll do it for today. So I hope y'all have a good one, and I will see y'all on Friday.
Have a good day.
You too.